Okay, can you hear me now? Thanks for letting me know. All right, so I muted my podium mic, so the previous instructor messed with my settings. Okay, I see a hand raised, but is it to let me know that you can't hear me? Or do you have a question? Okay, well, oh, I see. It's probably to let me know that you couldn't hear me. Thanks for letting me know again. So we're gonna go through chapters 1 through 5. Starting with state equations, then we're gonna move on to the bigger picture of solving the total response, which is including natural and forced. Talk about transfer function poles and zeros, order systems, which will only cover first order and second order, first and second. Higher order systems will be excluded, and then finally a review of block diagrams. So hopefully this will just be a good picture of what we've done so far. So first of all, we're going to talk about state variables. So state variables are the minimum set of variables required to fully describe the system, or the smallest set of linearly independent system of variables. And the way we want to think about it is that we always set our highest derivative, like this is the nth derivative, is always going to be equal to a function of all the lower derivatives. So maybe the n minus 1 all the way to the function and a function of our input. And that's one. The other one is the number of degrees of freedom. So I think it's, shoot, I don't remember the off the top of my head what it was. I think it was the number of degrees of freedom multiplied by the highest derivative minus 1, something like that. I'll probably update that later. So in the case of like the two mass spring dampers, we have 2 degrees of freedom. We have second order derivative, and we have 2 states per degree of freedom. So we add them up to get or fourth order system. So actually, I would think of it more like the total number of state variables is going to be your order. Anyway, so the future state of the system is found using the current state and is expressed using the state and output equations here. And the reason why we like that is because we put this into a first order differential equation in the matrix form. And the solution to a first order differential equation is easy to solve. This is our output equation. And think of x here as I state variables x1, x2, all the way to xn. So when you take the derivative of it, you're taking the derivative of every single state variable. Note that the way state variables is defined is also not unique, like here I can say that one way of defining it is I can say x1 is equal to position, x2 is equal to velocity, and then x2 dot is equal to my differential equation, which is acceleration. But another way of framing it is I could say x1 is equal to x dot, x2 is equal to x2 dot, or x1 dot is equal to my acceleration. You could define it however you want. The eigenvalues will remain the same. So then like maybe I could also define it as this. X1 is equal to x1 or x plus x dot. X2 is equal to x dot minus x, something like that. As long as the state variables are linearly independent from each other, then you can define them however you want. So the C matrix, so finding A is just basically finding how the state variables are related to each other. The B matrix is how the input enters the system, and the C matrix is based off of what I want as the output. So if I specify that, then you can determine what C is. So if I say C is equal to, then let's say Y is equal to X1 plus U, then my C matrix is going to look something like this 1 0. If I'm using X1 X2 as my, if I'm using actually let's if I'm using this example here, then my C matrix is going to look like this. And then my D matrix is going to be equal to 1. And in this case, D's not a vector, it's just a scalar. Okay. All higher order systems can be expressed as a first order differential equation when expressed in state space form and is easy to solve. And that's why we like the state space form. So that wraps up state space. The next one is just the total response of a system. So the total response of a system, and this is using this is the time domain solution. And this is our frequency domain solution. And the way you get that is just you take the Laplace transform or the inverse Laplace transform, you can get one of the other form. And then, so note, because of the B here, this right one's the forced solution. This is the forced. And this is the natural, which is dependent on the initial condition. You can tell by the initial condition right here. So this is the relationship between the time domain and the frequency domain. And if we break down each component, if we look at the natural solution first, the natural response is dependent on the initial conditions in the time and frequency domain. So this is our natural solution. And the reason why we like this form is because when we do eigenvalue decomposition of A, we can rewrite e to the at as v e to the dt v inverse. One thing to note that even though the frequency domain is in the S domain, we still have our initial conditions here, which is in the time domain, but these are just constants. It's like a x naught of 0 is equal to x1 of 0, x2 of 0, all the way to xn of 0. Now that I've taken 564 should have covered this, you can decompose your A matrix into a set of eigenvectors with the corresponding eigenvalues in this diagonal matrix for all real and complex conjugate eigenvalues. So then we can use this decomposition as our solution, natural response solution. And the textbook defines the state transition matrix as this. So I guess in the previous slide, I already covered it. We can decompose it like that. And the natural response of the output is this form here. C times your state transition matrix multiplied by your initial condition, which is what we saw earlier on the earlier page. What we actually saw earlier was x of t total. So the total solution is going to be equal to v of t times x naught plus that integral term here. And basically we just took this x total, multiplied it by c to get the output equation. So then this is then subbed into this here, and it's multiplied by c. So you can find the natural solution in the frequency domain using this format as well, where you have your S minus A inverse multiplied by your initial conditions, and then you multiply that by C because Y is equal to CX plus DU. So you just apply that C and you can get the Y natural solution. Then you take the inverse Laplace transform to get Y of T. Yeah.
Only about terminology, but it's just that the state transition matrix is phi t, and then previously I've seen it in some contexts where A is considered a state transition matrix essentially, because if you consider if you consider like no in a system with no input, B ut is non-existent, then A is simply just driving state transitions. So can you can you clarify like that A is not a state transition matrix?
Yeah, A is not your state transition matrix. So state transition matrix, if I say, so A is just basically just a matrix that, so I think maybe when I say state space, I want my state space, then I want you to specify A, B, C, and D, and these are your matrices. But then when I say state transition matrix, and this is the way it's defined in this class and in 547, actually in all controls classes. So this is a standardized definition. These two are standardized definitions. Then you think of B of T, which is equal to E to the AT, and you use this A here. So that's how they're related. Yeah. So
in the case where there's no input at all.
Oh, there's no input. Oh, yeah. So then your state transition. So your state transition matrix is just this definition here. Even if there is no input, we just don't use it, I guess. If that makes sense. So we don't use the state transition matrix if there's no, oh, sorry. We don't use the state transition matrix if there's no initial condition to solve anything.
No, that makes sense. Like that, there's no initial condition. But
Yeah.
What I'm saying is that it's what's confusing is that if you consider a case where there's no input.
Oh, where there's no input? Yeah.
But there are
Yeah.
it's matrix A, then and actually I see. So like I guess what I'm saying is like x dot t is going to take you from state xt at t equals like 1 or whatever.
Yeah.
So in a way, x dot t equals axt. A is driving state transitions.
A is driving state transition. What do you mean by that? I'm not quite following. Yeah.
X dot t is going to maybe I'm just not understanding something very basic here, but like x dot t will like move you from xt1 to xt2.
So x of t is going to give you x1 of t. It's going to give you all the solutions to each state. Okay. And then you have your state transition matrix multiplied by your initial conditions plus the integral of, I guess, like a modified state transition matrix. I'm not going to write the whole term because I'm running out of space. So I guess. Okay. Yeah, maybe we can talk after class. I think for now, just take the definition for granted, and then we talk about this later. Maybe like forget about this definition here. You don't need to know that's called the state transition matrix. Just know how to Just know, mainly the most important thing from this whole slide is this relationship. These two highlighted points is that e to the at can be decomposed down like that. And that's the most important aspect of it. They just use state transition. They just use this definition here to just shorten that notation and make so you don't have to write out e to the at every time. I don't know why, but I'm just following the book definition. So this is just going to be c e to the at multiplied by x naught. And this is just derived from the first order differential equation solution of the solution to x dot is equal to x. The solution is x of t is equal to e to the minus t. So maybe x dot to the ax is equal to e to the minus at, and that's where it comes from. Okay. Oh, okay. So that answers your question. That's where it comes from. Yeah. So then in the matrix form, you get x dot is equal to ax, and there's no input. Then we get x of, and these are vectors now. X of t is equal to, yeah. And actually, I think it's at, not minus at. Yeah. Because then we think about it, we take the derivative of x, then x dot is equal to a e to the at, which is equal to ax. All right, cool. I'm glad we answered that question then. All right. I think sometimes I just take things for granted. So then similarly with forced response, you look at the forced response solution, you get this integral, and then you can find it by solving it in the time domain or taking the inverse Laplace transform. I personally think solving it this way is easier. This is the easier way. But both ways are still valid. And on the homework, you did this way as well. It's a little bit painful. Sorry, but I think it's still good to know and to just solve it once. So then finally, we're going to talk about transfer functions, and this is going to encompass Laplace transform. So the reason why Laplace transform is so useful is it explicitly separates all these higher order differentials in the time domain into a single variable in the frequency domain. And to express those derivatives in the frequency domain, we just multiply it by s. Or to take the integral of it, you divide it by s. So it's very useful. And in the case of, let's say, x double dot is equal to u, and we take the inverse, or we take the Laplace transform of it, and this time we do have initial conditions. We get this minus s times the non-derivative, so x at time 0 minus the derivative at time 0 is equal to u of s. Then when we get that, when we separate it, we can't actually fully separate it explicitly because of the initial conditions. We get u of s over s squared plus minus s x naught minus x dot of 0 divided by s squared. Well, the thing is, we know that this term here is our forced response. This is the forced response. And this is going to be part of the transfer. This is going to be the transfer function because the transfer function implies that we have this input here. So 1 over s squared is our transfer function. And this here is just our natural response. I'll do a different color. Natural. Because you can see it's only dependent on our initial conditions. But in both cases, when you're looking at the force over the natural, they share the same poles, meaning they share the same transient behavior or similar transient behavior, meaning they'll have the same decay rates, they'll have the same oscillation. And basically, you just use the Laplace transform tables, and you use these properties to take the Laplace transform, get your frequency domain, rearrange it such that you can use this table, and then you take the inverse Laplace transform to get the time domain solution. So basically, yeah, this summarizes that. Laplace transform in the time domain, you get the frequency domain, which is s. And just to note, s is equal to some real number plus j omega. And then you apply your input and or initial conditions. Then you take the partial fraction expansion use tables 2.1 and 2.2, take the inverse Laplace transform, and then you get your ordinary differential equation in the time domain. So that's what Laplace transform is useful for. Next, we're going to talk about poles and zeros. So poles and zeros are just basically defined using the transfer function, where poles are the roots of d of s. In other words, values of s that causes d of s to equal 0. Basically, this is also the eigenvalues of A. So these are your eigenvalues of A. And you can find the poles by solving the determinant of Si minus A is equal to 0. And then the zeros are the roots of the numerator terms or the numerator polynomial, or in other words, values of s that causes the numerator polynomial to equal to 0. Oh, here I have poles are the eigenvalues of A in state space, and poles affect the transient response and stability, while zeros affect the transient response in the scale of the output. And you also want to include any pole zero cancellation terms in the equation. One thing to know about this is that if all your poles, your set of all poles are set of all real eigenvalues are less than 0, then it's stable. And if at least one real pole is, or if at least one of your poles has a positive value, then it's unstable. So that's all you need to know about poles and zeros up to this point. Moving forward, we're going to talk about order systems. And I know it seems like we're almost done, but we're only on page 15 of 24. All right, so first order systems, we have this where we have this first order system B over S plus A, and these are the definitions for it. Time constant is tau is equal to 1 over A, which is the time it takes for a step response. So this is going to be based on a step input. And so you have these definitions. Tau is going to be 1 over A, so it's going to be dependent on the pole location. Rise time is also dependent on the pole location, and settling time is dependent on the pole location. Makes sense? Poles affect the transient response. Same with zeros. This here assumes that there are no zeros. Once you add a 0 to this definition no longer holds, but you can use it as an approximation for your performance metric. Usually adding a negative 0 to the system here will make this perform faster, so you're actually going to reach 63% of your final value a little bit faster. Your rise time is going to be a little faster. Settling time might be a little longer or faster, so you need to use simulation to figure out how long it takes. Now, second order systems can be rewritten like here. So this is assuming that it's a step input, no zeros again, and that we have this generalized form here where our system can possibly oscillate, and if it oscillates, it has a natural frequency. If it's underdamped, it has a damping ratio and a damped frequency. And the damped frequency is what it's the oscillation you'll observe, because damping does take away some of that. So it does reduce the oscillation speed, so it's going to reduce the frequency a little bit, which I think is intuitive. General second order system is overdamped when your damping ratio exceeds 1, underdamped when your damping is between 0 and 1, and undamped when damping ratio is equal to 0, and critically damped when damping is equal to 1. So this is the only scenario where these two are the only scenarios where you'll see oscillation. One thing I want to note about, okay, actually I'll finish this page. And I'm going to talk about DC gains, about first order, second order systems, and higher order systems, because I'll show you the way I find DC gain. And this should also help you with your homework. For underdamped second order systems, the output response for a unit step input is this equation here. And you can use this generalized equation once you get the numerator terms like that, and then you pull a k out, then this is going to be your response for underdamped second order systems with no zeros. And you get this form. Phase shift is dependent on the damping ratio only, and you could just plug this in. No need to do the whole step of partial fraction expansion if you have this exact form here. So then on second order systems, these are the performances. You have peak time, percent overshoot, and then let's say I have percent overshoot given and you don't have damping ratio. Well, percent overshoot and damping ratio are only functions of each other. You don't need any other metric. So then you can then determine damping ratio with percent overshoot or percent overshoot with damping ratio. Settling time is this equation here, which is going to, and then there's no analytical equation for rise time. One other thing I wanted to note that I don't have on here is that when you're looking at second order systems and you have your poles here, just as a little reminder, the height here is your damped frequency. So this is the imaginary axis. This is the real axis. And then we have our minus zeta omega n. And that's the relationship between your damped frequency and your natural frequency. And then this here is your omega n, I believe. I'm gonna roll with that. Anyway, so that's the relationship. So then this is, I'll just write it out. So, okay, I cut that out. I cut the higher order systems out, which is good. You don't need to know anything about higher order systems. Won't be on the exam. Actually, maybe I'll just do it on this page. No, not enough space. I'll add a page. All right. One thing I want to talk about is DC gain because I feel like I talked about it, but I never wrote it down formally. So the way I find DC gain is by applying the final value theorem. And I'll explain why this works. So basically the final value theorem states that if I have a function, and I'm going to just use output here, y at steady state, the output at steady state is going to be equal to the limit as s goes to 0 times s multiplied by y of s. I just like to think of it as y at s is equal to 0. I don't care much for the official definitions. And basically, another way, a shortcut of finding DC gain is just basically letting g of s is equal to 0 is your DC gain. And I'll show you why. Basically, what we're doing is this. G of s is equal to y of s times u of s. So then when we rearrange this equation, we get y of s is equal to g of s multiplied by u of s. Now let's applying a unit step input. U of s is equal to 1 over s. Because in the time domain, U of t is equal to, and I guess formally it'll be 1 for time greater than 0 and 0 for time less than 0. But for all intents and purposes, basically u at infinity is equal to 1. So it has a magnitude of 1, input magnitude of 1. Now, when I find y at infinity, we get limit as, oh, and I see why we have this. This should be s at equal multiplied by 0. So guess I'll remove that. Okay, limit as s goes to 0 of s multiplied by g of s multiplied by u of s. And here, I just subbed in y of s into, or I just subbed in gu in place of y. Then I plug in my step input. Limit as s goes to 0 of s multiplied by g of s multiplied by 1 over s. And here our s's cancel out. And we get basically g at s evaluated at 0. Now, the reason why this works as our definition of DC gain is because DC gain is defined as the output at steady state, which is time at infinity, divided by our input at steady state. Which is equal to y at steady state divided by u at steady state, which is equal to y at infinity divided by 1, because our input is 1, which is equal to y at infinity, which is equal to g at 0. Does that make sense? So when I find the DC gain of a system, I can do it immediately without applying all these steps. If I have the transfer function, I just apply s is equal to 0 and I get the DC gain. And that's my shortcut. So maybe to really emphasize this point here, g at 0 is your DC gain. So that general second order equation I give you guys, let's say g of s is equal to k multiplied by omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared, where I say this is your DC gain. Well, when we do g of 0, we only get k because the omega n squareds cancel each other out in the numerator and denominator terms. So you don't even need to pull out the k here if you want to find the DC gain. Just plug in s is equal to 0 and you get your DC gain. And that's the relationship between of why I also pull that k out to get the numerator and denominator terms of the non-s terms to be the same. Any questions? Yeah.
U of s, or sorry, the y of s equals u of s and g of s. Just seems like if you did the algebraic manipulation up there, then you would have y of s equal over g of s.
Oh, sorry. So g of s is just equal to your output divided by your input, which is defined by your out y of s, which is over u of s. Then you just cross multiply.
G of s equals y of s.
Oh, yeah. My bad. Thank you. Yeah, I see it. Oops. I don't know what I was trying to do there. There you go. Let's just leave it like that. Thank you. All right. So we got that. Yeah. Anyway, so that's DC gain. Basically, short story is just plug in s equal to 0 for your transfer function, you get your DC gain. And this only applies for stable systems. Unstable system has infinite gain. This is only for stable system. Only for stable systems. For purely oscillating systems like marginally unstable systems, I guess in a sense you can find the gain because the max peaks will be your output, but I wouldn't really worry too much about that. Because it's not staying at a single maximum value, so there is no steady state value, so you can't compute that. Anyway, now moving on to your block diagrams. These are your tricks here. You have your cascade form where you just multiply them when they're in series. Parallel, you can add them up. And feedback form here. So this plus minus sign corresponds with this minus plus sign. So if you have a minus, you pick the plus sign. If you have a plus in the feedback, you use the minus sign. And your open loop transfer function is going to be G times H, not just G. And then your closed loop transfer function is this definition here. Finally, when here's some extra tricks. You're also welcome to do the signals method as well. Instead of doing block diagram, signals method is also okay. It's whatever method you feel the most comfortable with. So just as a little recap for signals method, if I define this as x1, then this is going to be equal to g1 x1, and then x1 is here. So then if I have x1 here as well, this point becomes g1 x1, and then multiply it by 1 over g. Oh, sorry, I don't have a g1 here, just x1 here. Then you get x1, which is good, and here we get gx1, which is also good. So my first hint for signals method is to apply them after summing junctions. Apply or define the signal after before summing junction. Define a signal either before or after at summing junctions. So define a signal at summing junctions depending on what your goal is at summing junctions. And you can also define them at pickoff points like the way I did here. Define a signal at pickoff points. And if you define too many signals, that's okay because they're redundant. You might just have x1 is equal to x2 then, and that's okay. It's better to have more than less. So then we were to check here, if we call this x1 here again, then at this summing junction we get, but you see this is a summing junction, so I need to define another one here, x2. Then this output is going to be equal to gx1 or plus or minus gx1 plus or minus x2. So then here I need to define x1 here. And if I push this g through the summing junction, well, this signal x2 doesn't contain g, but then g is being applied here, so we need to divide it by g. So then we get g multiplied by plus or minus x1 plus or minus 1 over gx2, which is equal to g plus or minus gx1 plus or minus x2, and we're good. It's all about maintaining equivalence when you're using signals method. I mean, and if you use visual block diagrams as well, it's also about maintaining equivalence, but the signals method is useful for checking, good for checking, and for solving as well. Finally, the last one is if you have summing junction with multiple signals, you can break the summing junctions up a little bit. So this is redundant. It's not needed, but maybe it'll be helpful to see feedback in one of the signals, for example. So can't really think of one off the top of my head, but if we have multiple signals here, let's say we have a feedback signal here, and then maybe we have another signal, and maybe we have a feed forward signal here as well with a block. Breaking this up will just make it more obvious that one of the signals is maybe have these added together. I mean, breaking it up like this will make it more visible that we have two parallel lines that can be added. So these two can be added, and this one can be fed back. And the reason why it's just nice is just because you can see now that we can just, it just simplifies the block diagram. Even though we have a redundant line, at least it makes it easier for visualization. It's going to be a plus sign here. Finally, we can simplify block diagrams to equivalent form and can use the signals method as well. So you can either put it into negative unity feedback, or you can put it into non-unity feedback. And then if you want to simplify it to a single feedback or single closed loop transfer function form TFS, that's also okay. The reason why we sometimes do this is because we have equations for it developed already. And one other note about block diagrams is like, feel free to just redraw the diagram. Like it may help to redraw diagrams, because sometimes the way something looks might not obviously look like a feedback system, but could be a feedback system. So if you draw like we're all accustomed to seeing this because in a way we're all trained to see that. We're like, oh, that's a feedback system. But maybe, you know, if I were to mirror this and rotate it 90 degrees or something like that, it might no longer look like a feedback. But so feel free to just redraw it to make it look more familiar. So that's it for the review. Hopefully this was a good summary of everything we've done so far. Up to midterm 1 material. Are there any questions? Oh yeah, so for rise time, questions about rise time being normalized to natural frequency. Yeah, it's normalized to natural frequency. Also, actually, good point. Maybe on the x-axis here, I'll write this is TR is equal to TR multiplied by omega n. And this is your damping ratio. So from your second order differential equation, you can find the natural frequency and damping ratio. And then from that, you can just work out the equation to solve for rise time and use interpolation if it falls, the damping ratio falls between the values on this chart. All right, so good luck on Monday. I'm going to make a formal announcement on exam logistics, especially for the online folks. And yeah, I hope you have a good and restful weekend. Oh yeah, no problem. I'll also upload the notes as well, right, after class.